So you can see here that there's a wide set of technologies that can be included in a hybrid energy system, and these are being considered for different applications and purposes today. They can also be connected at different levels of the energy system, including on the bulk grid or in a distributed application, as Sarah mentioned in her introduction. And of course, they're also very popular in remote microgrid applications for those regions that are not fully connected to a larger grid network. Finally, hybrids can be designed to generate electricity or other co-products, including energy products, but also non-energy products. So this is really a huge suite of technologies and a huge suite of applications. And to try to draw some bounds around this and make it more of a manageable presentation, the focus today will really be on renewable energy generation sources combined with energy storage technologies that are combined to form a hybrid technology that is connected to the bulk power system. So we're really talking about utility scale deployment of renewable energy and storage combinations, or perhaps multiple renewable energy technologies being combined together. The focus today is also only on hybrid systems that produce electricity as their only output. This is really a subset of the hybrid systems being considered today, and I don't mean to suggest that any of the other hybrid applications are less valid, just making it clear kind of what the focus of this presentation and our research to date has been. So if we look at the technology combinations that have been proposed in the US and internationally, what we see is that there really are a diverse set of technology combinations that are being considered. So this nodal diagram divides technologies into three categories. The blue nodes are the variable renewable resources, including wind, PV, and run-of-river hydropower. The green icons show energy storage technologies bucketed into pretty large categories, but ultimately this captures all of the energy storage technologies that are being deployed on the grid today. So batteries, compressed air, pump storage, hydropower, even things like ultracapacitors and flywheels. And finally, hybrid energy storage systems, where you would be combining two of these energy storage technologies together into a hybrid of its own based on energy storage only. Finally, the orange icons are what we would refer to as sort of less variable renewable resources. These are renewable resources that are more dispatchable, such as geothermal and reservoir hydropower, but it also includes a number of hybrids in themselves. So PV plus battery is showing up here as its own icon because there have been proposals that look at combining PV battery with other resources rather than stopping once you get two technologies together that would form your hybrid system. Similarly, for wind plus mechanical storage, which could be compressed air energy storage or pump storage hydropower, for example, and also concentrating solar power with thermal storage. These might be hybrids in themselves, but they also can be combined with other technologies to try to further increase the value that they offer to the energy system. So if you look at the arcs that are connecting these various nodes, we see that there is a huge number of technology combinations that have been proposed. Most of the arcs are coming out of the wind and PV nodes, which I think speaks to their cost competitiveness on their own, but also their declining value as their penetration increases. So there's more of a motivation to be combining these wind and PV resources with other technologies that can try to avoid some of the declines that we would see otherwise in terms of the energy value they offer, in terms of their alignment with demand and things like that. We also see that in many cases, we do tend to propose combining these variable resources, the blue nodes, with energy storage technologies in green, but also, blue to orange, blue to green, orange to green, really every combination exists. All of these hybrid systems are ultimately motivated by sort of two common factors. You're either looking to combine technologies whose resource profiles are complementary of one another. So they're generating at different times of the day, different times of the year, for example. That's an application for PV wind hybridization or PV run-of-river hydropower generation hybrids. The second motivation is really to look at technology combinations where the capabilities are complementary to one another. So this helps explain the VRE plus storage hybrid systems where you're combining low-cost, low-emitting resources that can generate electricity for you with an energy storage technology that helps you make it more dispatchable, more controllable, and shift that energy generation into the times of greatest grid need. So while there are many technology combinations being considered, they really can be explained by just those two motivations: complementary resource profiles or complementary capabilities. So the key questions related to hybridization, this is sort of a subset of what I hear most often. I think it is consistent with what we just saw in the poll responses. As industry interest in these generation plus storage hybrid grows, we want to try to understand what is the underlying motivation. Is this interest driven by incentives, or are there cost and value synergies that are really driving hybrid systems, which would make them more long-lasting as a grid solution. What are the important aspects of hybridization that influence their competitiveness, especially when you compare a hybrid project against an independent deployment? So separating your PV and battery into their own deployments rather than coupling them into a hybrid configuration. Third, under what conditions does it make sense to combine these utility scale generation and storage technologies? Are there thresholds that help us understand when hybrids really kind of tip the scales and become the competitive technology going forward? And finally, does the optimal hybrid project vary based on perspective? So in terms of if you're the plant owner or if you're the grid operator, do you want to see different characteristics in your hybrid systems on the grid? The key takeaways from the presentation, this is sort of getting ahead of myself, but I just wanted to put the punchline up front to kind of tee up what we'll be talking about for the rest of the presentation. First, what we're seeing internationally, and again, consistent with your poll responses, is that hybrid projects combining PV, wind, and storage in various combinations appear to be the most commercially viable today. But we do see a very wide range of hybrid systems that are being proposed and built, especially in the grids that are growing to meet increasing electricity demand. The second key takeaway is that adding storage to variable resources can facilitate many benefits in the form of renewable energy integration, which means both aligning your resource with the load, but also mitigating some of the short-term variability that we would see otherwise in variable resources. Second, increasing capacity factors. So our total output goes up when we're able to capture energy that would otherwise be wasted. Third, by combining these resources, we're able to localize some of the high value services. So one power plant can provide both the energy and capacity and ancillary services rather than relying on different projects to provide those different services. And finally, as Sarah mentioned, cost savings can be realized, especially for those cost categories that are applied on a per project basis rather than a per technology basis. Finally, I do just want to note that many of the benefits attributed to hybrid systems, including some of those in the bullets just above, can also be achieved with separate projects that are coordinated at the grid level. So while there's a lot of interest in hybrid systems and they do offer a lot of value, I do just want to make it clear that they're not always the right answer. There are greater benefits that can be achieved through increased flexibility in separate projects under certain grid conditions. So I have just a couple of slides walking through some of what we're seeing today on the grid, both in terms of the projects that are online and also those that are being proposed for interconnection today. So these are really the near-term hybrid applications, trying to understand what they look like today and how they might evolve over the next few years, using the US as an example. So this chart here shows the capacities for hybrids and co-located resource projects in the United States that were online at the end of 2019. So this is consistent with what we've already talked about. The technology combinations that appear to be commercially viable today include combinations of PV, wind, and storage technologies with select applications for fossil and storage applications as well. What we see if we just look at a single row, so for the PV storage projects, on the far right-hand side, we start to get a sense of what the storage deployments look like when combined with PV or with wind in the next row. So PV plus storage tend to involve modestly sized battery storage technologies. The average duration is shown here as 2.6 hours. That's really sort of a weighting factor. In general, most of these PV battery projects are using 4-hour battery technologies to couple with the PV. As Sarah alluded to, this is because of declining costs, but also the value associated with being able to span that peak time period in the late afternoon and into the early evening. Wind plus storage projects tend to have shorter duration storage associated with them, and that's because in general, these hybrid projects are designed to try to capture ancillary services benefits which occur over shorter time scales. So there isn't as much of a need or benefit of having a 4-hour storage technology when you can use something much shorter to capture this ancillary services value. Finally, the bottom row points out that you don't need storage actually to form a hybrid system. What we're seeing in the US and also internationally is that PV wind combinations are very common as well. This is again trying to capture that the complementarity and when the PV and the wind are generating. So it's very beneficial if you can find a place where the PV is bright during the day, of course, but then the wind is maybe blowing more at nighttime, and that way you can maximize your utilization of the transmission network. You can also maximize your use of land in that case as you intersperse the PV panels around your wind turbines, trying to use that land as efficiently as possible and also your transmission networks. And those are two of the main constraints that we see in trying to build new generation technologies. If we look into the near term, we see slight changes in what we expect for PV, battery, and wind storage hybrid systems. This points to both the fact that we expect hybrid systems to capture a growing share of new capacity, but also that their role will be evolving somewhat. So what we see is that a lot of PV projects are being proposed to be coupled with storage. This speaks to the synergies between PV and battery technologies that I'll cover in a couple of slides. A smaller share of wind projects are being proposed for coupling with storage, but we are also seeing a move towards these longer duration storage technologies in the proposed projects. So wind might be moving closer to the model that we're seeing for PV, and that you're using the battery not only for these ancillary services products, but also for some energy shifting applications. In terms of what's driving these trends, I think there's a variety of factors. Policy is playing a role in the United States based on incentives that we have to reduce the battery costs when it's coupled with renewable generation, but it's also being driven by grid needs. These independent PV and wind projects are losing their value as more and more of it enters the grid, and storage can help mitigate some of that declining value. We're also seeing that there are cost synergies that help drive some of these deployments. So if you can share costs between them, that means you can build PV and battery together at a lower cost than if you were to build them separately. Finally, just one thing to point out is that it's a little bit hidden in this chart, but the amount of standalone storage that's being proposed to be built is also larger than what we're seeing in these hybrid applications. So again, not to say that hybrids will be the only thing that's built in the future. Standalone storage still has its own value as long as, in addition to the standalone PV and wind, which we're seeing kind of these light shades on this chart. In terms of how these projects are being compensated, there are a few different models for the power purchase agreement prices that we're observing in this case for PV plus storage projects. In general, on the continental United States, we're seeing, so the sort of the larger grid network in the United States, we're seeing a convergence towards about $30 per megawatt hour for the PPA prices. This reflects a variety of different models. In some cases, the storage is just bundled into the energy price, and it's compensated similar to how the PV would be. So we're really just looking at the increased energy production as justifying the adding of the storage component to the hybrid system. In different models, we're actually carving out the storage to be treated slightly differently. So it is receiving that energy revenue, but maybe it's receiving most of its energy revenue during peak periods. And that's showing up in the PPA agreement where we see that the prices are very high in the afternoons throughout the summer, for example. And presumably that's where storage is really capturing all of the value and justifying the inclusion in the hybrid project. A new model that's emerging in the United States is actually to carve out separate compensation for the battery based on the capacity contribution. So these are fixed payments that basically say, we want the storage to be available at these very high stress periods for the grid. We will offer you a very large payment to have that storage available. And in that case, that's folded into the PPA agreement. That's where storage is earning its keep, and all of the additional energy production that occur throughout the year, that's just sort of a benefit on top of all of the capacity compensation that's being made to the storage. Finally, before I move into kind of the ongoing research, just to look internationally, so rather than being restricted to the US, looking at abroad to see what types of hybrid projects we're seeing there as well. In one sense, it's more of the same. As Sarah mentioned, there's expected to be a significant growth in PV wind hybrids in India, potentially reaching almost 12 gigawatts just in the next couple of years. Again, trying to leverage that maximizing approach to using our land and our transmission networks efficiently. So this is sort of more of what we're seeing in the United States, but at a larger scale internationally. We're also seeing a diverse set of hybrid projects, some of which are not competitive in the US today. This is a PV CSP hybrid that is being built in Africa. That's meant to operate as sort of a baseload plant there, again, with very low emissions and very high reliability. And finally, we're increasingly seeing proposals and projects where PV is being floated on hydropower reservoirs to try to maximize some of the efficiency gains of having the cooling of the reservoir coupled with the PV helping to avoid evaporation. More on this later when Sika presents as the second panelist today. So just a couple of slides highlighting the research that NREL has been doing around understanding the motivations for hybrid systems. This is going to be focused on solar plus storage projects. I think that's where a lot of the momentum is in the United States today. But in general, some of this can be expanded into other renewable energy plus storage projects as well. So the first point to make is just that how you form your hybrid system can make a big difference in terms of the types of synergies you're trying to capture relative to independent projects. One model uses separate inverters for both your PV and your battery technology. This offers additional flexibility, and it also allows us to use the existing participation models today. So in this case, you can use the PV and treat it as an intermittent resource in the way that we already do when we connect PV to the grid. You then treat your battery separately as a storage technology. So you're leveraging those existing participation models. Each resource can really operate in the way that maximizes its value. And maybe you're trying to understand how they work together, but ultimately you're able to operate each of them in the way that is most beneficial and therefore maximizes the value of the plant. The other model is to actually have the PV and battery technologies share an inverter. This introduces new cost savings that can be leveraged. It also introduces new value synergies in the sense that you can capture more of that PV generation and use it at a later time at a higher efficiency relative to having two separate inverters. But this also introduces some new interconnection challenges. How do you treat this resource where the inverter is representing both a variable resource and a storage technology? So flow is happening in both directions. It's dispatchable, but it's also not entirely firm. So while there are additional benefits here, there's also potentially additional challenges when you move into this so-called DC coupled PV battery system. In terms of the motivations for both of these technologies, I think the main one is really trying to capture shared costs and therefore reduce the total project cost. The panels to focus on here is the comparison between the hybrids in the middle and separate projects on the right. So in this case, we're seeing that hybrid projects are cheaper because the stacked bars are lower than if you were to deploy similar projects separately on the both power systems. The main reasons for these reduced costs have to do with sharing the electrical balance of system costs, which is again applied per project. We're simplifying things by having all of this deployed at one time and being able to install it together, which reduces the total project cost. And in the case of the DC coupled system, as I mentioned on the previous slide, there's additional cost savings that can be captured if you're avoiding one of the inverters that would otherwise have to be built. In this case, you could choose to either install a PV inverter or a battery inverter. They would both work and they would bost reduce your total project cost because you're just avoiding that hardware component. The second motivation is looking into these value synergies. There are many of these, especially when you start to couple PV and battery systems together. The first is highlighted on the left. This is sort of a dispatch plot where you can see the legend at the bottom, but in general, the blue is showing you battery discharge. The warm shades are showing you the available PV resource. And what we're seeing is that in the middle of this day, the PV resource declines rapidly. The battery is able to absorb some of that reduction in output so that we don't miss these periods when there might be a lot of value or when the grid is counting on the PV resource being available. So in this case, the battery is really helping to improve dispatchability and also avoid any forecast errors or periods of lower radiance in the middle of the day when the PV resource would be beneficial. Another benefit is looking at capacity factor improvements, so increases in overall output. Here what we're seeing is that the inverter is capping the total output, and all of the yellow bars here are wasted energy that if we weren't in a hybrid, it would just be lost. In the hybrid case, though, we can divert this energy into the battery and therefore make it available later in the day, later in the evening periods when solar is no longer available, but demand is high. So we're not only increasing the capacity factor, but we're also enabling energy shifting, which is making the PV resource available when we need it to meet our loads. This is a dynamic that's especially important when we get to higher PV penetrations, maybe not as important in the near term when we haven't yet shifted the peak demand and sort of that high stress period into the evening hours. So again, just noting that hybrids aren't necessarily the right answer until we've gotten to this higher PV penetration, and unless we're building our systems in a way that's really enabling us to shift extra energy into those hours of high stress into the hours when we really need it on the grid. So if we take all this information together and try to understand the deployment potential for PV batteries, this is an example output from what we've recently done in our resource planning modeling tools at NREL. Basically what we're seeing as we look forward in time, if we assume those cost savings I presented, if we assume those value synergies, or we allow those value synergies to be represented rather, we see significant potential for hybrid deployment. So by 2050, almost a third of our total PV capacity is actually taking this hybrid configuration rather than separate deployment. So it's capturing those cost savings and also the value synergies. It's not completely replacing PV, but it is serving a major role on the grid, showing that this potential for hybrid deployment really does grow over time, especially as the technology costs come down, especially as we're able to share costs between the two projects. So this is just the same key takeaway slide I presented at the beginning. Again, what we're seeing is that PV, wind, and batteries are sort of the most common projects to be deployed in hybrid configurations today and in the near term. This is because of the variety of benefits that they can produce by enabling renewable energy integration, making it easier to accommodate additional variable resources on the grid, increasing the total renewable output, which can grow to a factor of 50% or more if you're sizing your components correctly, being able to capture these high value services, and then of course the cost savings that can be achieved by combining these technologies into a single project. So from there, I'll hand it over to Sika, who's going to talk about a slightly different hybrid technology.
Thanks, Caitlin. So as my slides have pulled up, I'll be kind of just specifically focusing on some research that we've been doing, exploring the operational benefits of floating solar and hydropower hybrids. So there's been a lot of interest globally in floating solar, specifically floating solar paired with hydropower, because of perceived economic, environmental, and social benefits. But there's really limited research out there on the potential value of these systems to potential adopters of this technology. So in this presentation, I'll kind of quickly walk through some of the research we've done on that. But before I go there, I will provide kind of some background on what the technology is in the first place for those who might not have heard of it, and then provide an update on the current market landscape for this technology. Next slide, please. So what is floating solar, also known as FPV? Next slide, please. So essentially, you have kind of the same PV panels you would be using for a land-based system, but so floating solar is an application of the existing PV technology, and you have the panels sited on a flotation device, whether it's a float or pontoon. So if you look at the figure on the top, it shows kind of an example float, and then you have this located on different kinds of water bodies, whether it's lakes, ponds, or reservoirs. And then you have mooring lines providing stability. And then this system is connected to transmission, and then it can serve or meet demand on the grid. And there's two main types we're seeing. There's this kind of more standalone system, and then we're seeing the more hybrid system increasingly in different parts of the world, but we're seeing some initial deployments in Southeast Asia specifically. And in this type, you're pairing the FPV system with a hydropower system. And this specific kind of hybrid type has been is of interest for many reasons, but I will highlight two key reasons why we're seeing interest in this technology next. So overall, there's several benefits of FPV, as I noted, but the key one, irrespective of whether it's a standalone system or a hybrid system, is around reduced land use. So utility scale PV deployment requires lots of land, and so countries that have land constraints because of just the limited land available, but also the land pressures because of the need to meet other priorities, whether it's agriculture, housing, forestry, has really made land expensive in a lot of countries in Asia. So there's a lot of excitement about the potential to scale up RE deployment to meet their growing energy needs while preserving land for other uses and kind of avoiding any land use conflicts. And then the rest of the co-benefits listed here, there are several that I could have added here, but I'm just highlighting some of the hybrid specific benefits listed there. And Caitlin kind of touched on this in detail, so I won't go into too much detail, but essentially for the FPV system, hydropower provides an opportunity for it to essentially operate as a dispatchable resource, which is of interest because of, concerns around the intermittency of the resource. And then for hydropower systems, it's especially of interest because in some countries in Southeast Asia specifically that might depend a lot on hydropower resources. There are concerns during the dry seasons around, threats to energy security and providing reliable electricity. So the opportunity to really supplement potential dips in hydropower operation with outputs from PV plants is really attractive. So going to the next slide, I'll just provide an update on the current state of global FPV deployment. So currently, we're seeing that in total installed capacity is at about 2.6 gigawatts, up from 6 megawatts in 2013, which is still quite small compared to kind of global solar PV deployment. But this industry is there's a lot of opportunity for growth because the estimated technical potential is about 7 terawatts. And so if you look at the figure on the bottom left, we see that there's been kind of consistent growth in the last decade or so in the industry. And majority of the installed capacity is located in Asia. If we click next, we can see that most of that deployment in Asia has been in China and a few other countries shown there in the figure on the bottom right. But we're seeing deployment starting to expand beyond the Asia region to Europe and parts of Africa. So when it comes to system costs, on average, FPV systems are still more expensive than land-based PV systems, but just want us to bear in mind that this is still an emerging technology and costs are expected to decline. On the other hand, we have seen kind of a wide range of system costs from about $500 to $3,000 per kilowatt. And these costs depend on a variety of factors, including kind of the country that the system is sited in and the actual kind of water body that the PV panels are sited on. In countries that may have kind of turbulent rainfall or typhoon seasons, for instance, there might be the need for added infrastructure to make sure that the PV system, the FPV system, is stable during those seasons. So if we go to the next slide, I'm now going to quickly walk through the research we did on to explore the operational benefits of hybridizing FPV with hydropower. So we essentially looked at 3 example systems. So this figure kind of just is a simplified configuration of a hydro-only system, where the generation mix doesn't include any PV, a standalone system where the FPV, you have FPV in the system, but it's really operating independently of any other generation. And then you have the full hybrid system. So thinking back to what Caitlin said, here you have the FPV essentially hybridized with a hydropower plant in this case. And the key difference here is that they share an interconnection. So essentially, when you're optimizing their operation, there will have to be kind of, so you would have to pick when and how you're using the PV plant as opposed to the hydropower plant in some cases. So if we go to the next slide, we explore this research question using the Engage model, which is a web-based platform that enables multi-energy sectoral planning. And it allowed us to do some production cost modeling for this very small model systems. And here I'm just quickly showing kind of some of the examples results you could get. So if you want more information about the tool, you can go to the link, but essentially we're looking at the dispatch for 1 week during the year, and this is the first week of January. And on the bottom of that figure, the colors correspond to the different nodes. So in dark blue is the hydropower plant, in yellow is the PV, in orange you have the coal power plant, and then the turquoise color is just the reservoir serving the hydropower plant. And if we go to the next slide, just highlighting some of our findings. Essentially, what you see here is on the x-axis is time, so that's January through December 2019. On the y-axis is PV generation in megawatt hour. And then the different lines which correspond to the different scenarios. So the solid line is the FPV standalone system. And then kind of your dashed line there corresponds to the full hybrid system. And you're not seeing the hydro-only system here because, as I mentioned, the hydro-only system that we modeled didn't have any PV in the generation mix. And I just want to highlight the differences in PV generation here. We're seeing that in the hybrid system, we are seeing consistently higher PV generation throughout the year, sorry. So next figure here, also just kind of showing the corresponding hydropower generation during the whole year as well. So again, on the x-axis is time, y-axis is the hydropower generation in megawatt hour. And here again, we're seeing differences in hydropower generation. So here you actually do see all the 3 scenarios. So again, in solid blue is the FPV standalone system. And kind of your dotted lines, you have the hydro-only system. And then in your dashed dotted lines, you have the full hybrid system. And we see that in that hydro-only system, you're really using a lot of the hydropower plant during kind of August to September timeframe. And then based on kind of the data we're using, later on in the year is when they typically have the dry season, and you see a drastic decline in hydropower plant operation. But when you have the FPV as an option, and then when you even have it fully hybridized, we see that the system chooses to optimize and actually use less of the hydropower resources during the late summer months, and instead uses more of that during the dry season. So it's essentially conserving water resources for use later in the year. So next slide. And here you see kind of similar figures. I just wanted to highlight the complementarity of these resources. So Caitlin mentioned that a key motivation for hybrid deployment is, that some of these resources really complement each other. So if we click through the rest of the slide, we see that, and this is just showing 1 month as opposed to the whole year. So again, on the x-axis is time, y-axis is PV generation on the top and hydropower generation on the bottom figure. And if we click through one more time, we can see that whenever you have increases in PV generation, you have them complementing each other with a corresponding decrease in hydropower generation. So the system is optimizing when to run PV generation versus running hydropower plants. And we see that in the last thing, looking at the figure, the bottom figure, looking at the hydro-only scenario, we see that it just consistently keeps operating. But once you have FPV as an option, and once you even fully hybridize, it really allows you to conserve water resources during this month. So kind of to wrap up my presentation, our modeling results indicate that hybridizing FPV with hydropower could reduce PV curtailment, so it could increase the value of the FPV asset. It can also conserve water resources. So in places that kind of have concerns about depending on hydropower too much, especially during dry seasons, hybridizing with FPV could provide an opportunity to really conserve water resources. And overall, just wrapping up this presentation, FPV is still an emerging PV technology. There's a lot of excitement and interest in the technology for several reasons that I've highlighted earlier, but there's a lot that needs to be kind of learned about the value that it could provide to the grid and to plant owners. Thank you. I'll hand it over to, I believe, Sarah at this point.
Thank you so much, Zika, and thanks, Zika and Caitlin, for those excellent presentations. And now we have some time for questions. I had a question actually for Caitlin. Do you need to have prior experience in your country on renewables and storage in order to procure a hybrid project?
I certainly wouldn't say you need it. Of course, it would help because a hybrid is just simply, it's combining those two resources together. So having some experience, I think, is helpful, but at the same time, deploying them together really helps avoid some of the challenges that we've struggled with over the recent years to integrate more and more variable renewables, for example. So it wouldn't hurt, but definitely it's not necessary, since we can design these projects in a way to mimic more conventional power sources, but using these cleaner resources and by combining sort of the low cost nature of one with the dispatchability of the other.
Thanks, Caitlin. And I mean, is operating a hybrid power project more challenging from a grid operations point of view?
I would say it depends on how it's built and also how the plant owner decides to operate it. So in theory, these resources can be dispatched in the same way that independent projects could be. If they're responding to the same grid signals, we would expect them to be operated in a pretty similar way and in a way that is very grid friendly. You want to meet those periods of high stress, and you want to conserve and hold back your energy during those periods where there's a lot of low cost generation available, because that's not good for you and it's not good for the grid either. That sort of indicates that there's already enough supply available, so it's better to shift that production into a period of higher stress later in the day. I think we're also developing these technologies in a way that they're somewhat out of the box. I mean, you can just deploy them with a control system that helps you optimize the systems without needing to know how to control each one individually. They're designed to respond to the signals and provide the benefits that the grid wants in a way that doesn't introduce a lot of complexity to the plant owner and the plant operator. So I wouldn't, more than anything, I think the more complex thing is building them in the right way and designing them in the way that maximize value both to the plant owner and to the grid, But once that's in place, I think operating them would be very similar to other independent projects and also other power plant types.
Thanks, Caitlin. And we have a question from Rogness for fossil and storage. What is stored, the energy or the fossil fuel?
So a not huge, but somewhat growing application in the United States is to add a battery technology to the fossil power plant so that the battery can respond to quick response signals, and it can help avoid ramping your fossil fuel power plant in a way that is damaging to its mechanical pieces. So basically the battery is meant to help you avoid otherwise induced operations and maintenance costs. In general, these tend to be fairly small batteries coupled with a much larger fossil fuel power plant. But it's the electricity that's being stored either, diverted from the power plant generation itself, which can also help with ramping, or stored from the grid. In either case, the real purpose is to avoid having to respond to any quick response signals from your fossil power plant because your mechanical pieces just don't really like doing that. So the battery can absorb that and try to avoid some induced costs otherwise. So yeah, sorry, the short answer is that it's storing electricity, not fossil fuel in that case.
Thanks, and we have a question from Ryan. What is the capital cost of 4-hour generation batteries? So those estimates range from $1,200 to $1,500 per kilowatt for a 4-hour battery. But maybe the operative question is, why are lithium-ion battery systems more viable than other technology types?
Than other storage
than other
technology
battery
types?
Yeah, than other battery storage technology types.
Yeah, I mean, I think it's partially price, but it's also partially, that we have the manufacturing plants set up for the lithium ion. We're producing them at a much higher volume than other battery technologies. So they've just come a little bit further down the learning curve. I wouldn't say lithium ion is guaranteed as the future for hybrids in any sense. We tend to include them in today's deployments because that's what we're seeing people building for the most part. But in the future, really what we care about in our modeling anyway is just the round trip efficiency and the cost. And we do assume that at some point there could be a transition in the chemistry for the batteries that are used. We're not capturing exactly what that is or when it happens, but just that, lithium ion batteries can't keep getting cheaper forever. At some point they plateau and another technology would have to come in. So I do think that that's one of the more common chemistries being used in projects today, but I don't necessarily think that it's the only one to be considered in the future.
Thanks. And we kind of have similar questions around PPAs. So basically, our PPAs right now, like renewable energy PPAs, are they engineered to take on the hybridization? And that's really across all technologies. We had questions about hydropower, FPV, renewable plus storage. I think maybe that would, Caitlin, that'd be for you.
Yeah, I think it's an evolving space. Clearly, we have examples of PPA structures that are able to accommodate the hybrid technology fairly easily. It ultimately just depends on what the hybrid is being designed to do and how different that is from separate projects. So clearly, we can absorb a battery technology and compensate it just for the energy output in the same way that we would a PV generator. In this case, all we're doing is augmenting how much we're producing because we have that battery there to either take in curtailed energy or take in periods of really high irradiance and low demand and shift it to another time. That's sort of easily compensatable within existing PPA structures. But if hybrids evolve more to be there as a firm capacity resource, for example, I think PPAs are still able to accommodate them, but it'll require a shift. We'll have to be modifying our PPAs so that the battery is compensated in a very specific way. And we are seeing that happening in the United States today. We have a very specific and sort of famous example in Arizona where the battery is only being compensated at very specific times of the year because that's what they needed it to do. They needed to have a firm resource available under the very, very high demand periods in the summertime. And basically the entire annual compensation happens in a couple of hours in the summer. So it might take some innovation, but I don't think there's anything about a hybrid that's so different that we can't leverage the techniques we're already using today for separate PV and battery projects, and in the future, other resources as well.
Thanks, Caitlin. And we have a couple of pretty specific questions about floating solar for Sika. So one is floating solar only viable in reservoirs, or can you cite it in the tail race? Two, I think that's below a dam. And then do you have any successful examples of floating PV in seawater, like salty water? So I don't know, they're really specific if you know those.
Yeah, I can give a little bit of insight into that. So kind of what I presented as there's several kind of designs of FPV systems coming online, but what we've seen at the moment is predominantly kind of FPV sited in reservoirs, but the space is really kind of expanding into looking at nearshore and offshore, and even beyond artificial water bodies. So to the second question, there have been installations on salty water and even installations on water bodies that are otherwise unusable. So in China, we've seen installations on kind of polluted coal mines, for example. And so it's not necessarily exclusive to reservoirs. The thing with reservoirs, though, is that if you do have a nearby hydropower plant, it offers the opportunity for hybridization. And to the tail race question, I think there have been a few feasibility studies, but we haven't seen as much deployment there. So the thing with FPV is essentially a lot of the initial deployment has been encouraged through government-funded research and support. And so we are seeing a lot of pilot scale projects, and those were the ones that kind of then moved. A lot of the pilot scale projects focused on FPV systems sited in reservoirs. So now support is also expanding to looking at alternative hosting water bodies. And so in the future, we may see kind of installations on different kinds of water bodies, but definitely not exclusive to just reservoirs.
And then another question on the environmental impact. So are there any concerns about, biodiversity or fisheries or with floating solar?
So the research in that is still ongoing. And so at this point, it's a bit inconclusive. We actually conducted some research last year looking at the potential environmental impact. We didn't conduct it ourselves, but we reviewed the research in this space, and it's still unclear on whether FPV systems improve water quality, affect aquaculture, or there's kind of a negligible impact or negative impact even. And so research is still ongoing in that space.
Yeah, definitely something to monitor. And then what governs the use of the storage system for ancillary services or for energy purposes? Thanks to Tom for your question. Is it in the PPA or the interconnection agreement?
It would be more in the PPA, and it would be more in, I would say, in the design of the system as well, which again, it feeds into the PPA. But ultimately, right, the provision of ancillary services is relatively modest in terms of your interconnection use. You're not sending a lot of energy that way. But you would want to design your system in a very different way, because you don't want a 4-hour battery to be able to provide a 30-second service. That would be a waste of sort of your investment in that case. So I'd say it mostly comes into play in the design of the system, which of course will then influence what your PPA looks like and the compensation for it as well.
So we're getting near the end of our time. So I think maybe we'll just close with a question, which is what circumstances should utilities and regulators consider hybrid projects, and how should they determine which combination is best suited for their grid?
Hybrid projects, I mean, I don't think there's a situation where they shouldn't be considered. If you're able to do it at lower cost and you're able to make all of your individual assets more controllable, that's a win for everybody. The plant owner now has more confidence in their investment. It's a lower risk investment because you can shift and sort of accommodate changes in market prices and structures. From the utilities perspective, it eases the burden a little bit of trying to optimize a suite of resources where a significant share of them are variable, for example. In terms of how you design the one that's most optimal, I think it really depends on what your resources are that's available. I think that's the primary driver. And then the second one is sort of how your net load duration curve evolves. So as you get more and more PV, of course, PV battery is going to make more sense because adding more PV to the middle of the day when you've already met all your load is no longer beneficial. If you're in a high wind region, I think those are the places where we're seeing a move towards hybridization as well, because you're already saturating those times when wind is producing. So I think it's mostly driven by your resource strengths in your region, but then secondarily based on how much you've already penetrated your grid with these variable resources.
Thanks a lot, Caitlin and Sika, for your presentations. Thank you so much to our participants for their awesome questions. A recording of the webinar and the slide deck will be emailed to attendees when we're done here. You can also find the recordings on the USAID NREL Partnership Learning channel. So stay tuned for our next webinar. Follow NREL on LinkedIn or Twitter, and have a great rest of your day. Thank you, everybody.